Hello, today I'm going to do a video looking at the different distributions that we meet in Stats 2. So here are our discrete distributions. The first of the discrete distributions is the binomial distribution. It's exactly the same as it was when we met it in Stats 1. So we're looking at the number of attempts at something and we're looking at successes and fails on a given number of attempts. The conditions are the same as they were in Stats 1, so the trials are independent and the probability remains constant. And to find the probability, either we use the formula in the formula book for the probability that x is equal to x, or we look up x is less than or equal to on the stats tables in the formula book. The other distribution that we've met, which is a discrete distribution in Stats 2, is the Poisson distribution. And the conditions for that is that the event occurs randomly in space or time, and it occurs singly, independently, and at a constant rate. Again, to find the probabilities, we're going to use the tables in the formula book for x is less than or equal to, or we can use the formula that we're given in the formula book. The normal distribution, which is the last distribution we've met in Stats 2, is for continuous data. To find probabilities for the normal distribution, we need to change it to the standardized normal distribution. That's the distribution with mean 0 and standard deviation 1. And we're going to use z equals x minus the mean over the standard deviation to change our x to a z value. And then once I've got my z value, I can use my tables. As you'll know from my videos by now, I always like drawing a normal distribution to help me once I've got my probability. And that's our three distributions that we've met in Stats 2. Now we're going to have a look at when we can approximate between them. So let's have a look at our discrete distributions first. To go from a binomial to a Poisson distribution, I can do that if np is less than 5 and n is big, so n is more than 50. And then we can use the approximation that the distribution becomes Poisson, where lambda is n times p. We can approximate between the binomial and the normal distribution. I can do that if n times p is greater than 5 and n times q is greater than 5. Then the approximation that we get is y is approximately normal, where the mean is np and the variance is npq. Because we've gone from a discrete distribution, so we've crossed this box that we had for our discrete distributions. Because we've crossed that box, we're going to have to make a continuity correction to account for the fact that we're going from a discrete number to a continuous number. The other way that I can approximate to normal is using the Poisson distribution. I can approximate between Poisson and normal if lambda is sufficiently large, and in this case it's lambda being greater than 15. I can approximate it to a normal distribution where the mean's lambda and the variance is also lambda. And again, because we're going from discrete to continuous, I'm going to have to make a continuity correction. So that's the approximations between the distributions. We can also do some things if we're looking at the sample means. So this is going from a continuous distribution because the mean is always going to be continuous. And we can approximate sample means to normal distributions. If I know that the population distribution is normal, then it doesn't matter what the sample size is. The sample means will form a normal distribution where the mean of the sample distribution is the mean of the population distribution, and the variance of the sample means is the variance of the population divided by n. If I don't know that the original population was normally distributed, I can't do this. But what I can use is I can use the central limit theorem, which says that the sample means will form a normal distribution, provided that the sample size is large enough. The bigger the sample size, the better the approximation, but it's a good approximation if n is more than 30. This is called the central limit theorem that we're using, and I use it because it's quite a common question if I don't know what the parent population is and n has to be large. In this case, the sample means form a normal distribution, where the mean of the sample means is the same as the mean of the population, and the variance of the sample means is the variance of the population divided by n. And that's all the different approximations and distributions that you'll meet in Stats 2. I hope that helps.